All right, let's answer some questions. A viewer asks, is Newtonian physics laws that say energy can't be created or destroyed valid in the case of dark energy? So this is a really fascinating puzzle, and actually it even stumped Einstein. You see, when Einstein wrote his field equations and applied them to the universe, he got cosmological equations that showed that the metric was open. What does that mean? It means that the growth of space and time itself kept going. The Einstein field equations give us a set of rules for how the metric grows with time, and it showed that everything started out as a point. That's the start of the equation, and then as you give it time, it grows. So what Einstein did was he actually applied a cosmological constant that subtracted off growth from the metric and kept everything static so that the universe was steady state. And so we never had it growing or shrinking, it just stayed the same. However, when Edwin Hubble later looked at galaxies far away and found out that everything that we thought was the Milky Way galaxy, some of that was actually galaxies outside of the Milky Way, when he looked at the data, he found out that a ton of the galaxies were redshifted and were receding away from us. And the only way that could be possible is if space itself is expanding, and thus in every direction other objects that are far away are receding away from us. There's only a few nearby objects that are blue shifted or moving towards us. Andromeda Galaxy is one. But if you look statistically, if there was no growth and no expansion in the universe, there should be just as many objects that are moving towards us or blue shifted as away from us, and thus being red shifted. So the evidence from astrophysics that we found, what happened was cosmologists later went back and found out, hey, the universe actually is expanding. And so the original assertion that the Einstein field equations had, that energy wasn't conserved and that the only thing that we could say is that the metric is open and that energy can actually be growing and created with this dark energy, that is still alive today. Now, there's another question about this. What about at really short distance scales? Energy can also be violated for really short distances and really short amounts of time. So even locally, energy conservation is not always obeyed if the time that it happens is less than the uncertainty principle. So yes, classical physics and energy conservation is only valid at ordinary scales, but the real workings of the universe don't necessarily obey energy conservation all the time. And then this person says, pick up a Bible. First of all, I've got nothing against religion. There's a lot of scientists, in fact, who've been very active in religion. In fact, Georges Lemaitre, the scientist who's responsible for the Big Bang Theory, he was a Jesuit priest. Isaac Newton was extremely religious. You know, just picking a fight with somebody and saying, oh, because you do science, you must be against religion, that's incredibly narrow-minded of you, Evan Buckley 410, to just assume that I'm atheist because I'm involved in science. As a matter of fact, I am not an atheist, and I do believe in God. So you shouldn't just assume things about people because they're scientifically motivated and fascinated with science. There's nothing wrong with being interested in science. There's no counteraction between science and religion. The two do not disagree with one another. I am not of the opinion that they disagree with each other. And so, yeah, that's all I have to say about it. Thanks for being narrow-minded, though. Not. All right, let's answer some questions. A viewer asks, why do electrons exist as a probabilistic wave function, but protons and neutrons not? What accounts for this difference? Actually, everything exists as a probabilistic wave function, even you. But there's a reason we can't observe it in larger objects. Even it's harder to observe with protons and neutrons. The equation for the matter wave is behind me. Notice that the momentum is in the denominator. That means the more massive an object is, the smaller that wavelength is. We can actually use electrons as microscopes because we can diffract off of their matter waves. Their matter waves are so large, we can actually use them. However, more massive objects have much larger momentum. And remember, that thing in the top is Planck's constant. So it's really easy to shrink it down. And even our own bodies have a matter wave, but they're too small to observe. Without a doubt, the most dangerous forms of radiation are HCE ions. And these forms of radiation are the kinds that astronauts can experience in space. What makes these so dangerous is that they're incredibly fast moving and they also have a lot of mass, so they carry a lot of momentum. But why do they have so much mass? Well, to start with, this form of radiation is not a photon. It's actually the nuclei of atoms. It includes the nuclei of atoms such as helium, carbon, oxygen, magnesium, silicon, iron, and even as high up as uranium. High energy photons knock electrons away from neutral atoms and ionize them, leaving only the nuclei remaining. These nuclei are then charged and they're accelerated by magnetic fields and thrown towards Earth.